Okay, so let's find a bunch of limits. These are all limits as x goes to infinity or negative infinity. Um, so let's look at the first one. As x goes to infinity, the first thing I notice is that the top, if I think of x being a really big number, like a million or a billion, the top would be some huge number and the bottom would also be some huge number. So as x goes to infinity, I would say the top's going to infinity and the bottom's going to infinity. And so what do we do in a situation like this? One thing to do is to divide the top and the bottom by something. And typically in examples like this, you just choose the largest power of x that you see. The largest power of x I see is just x. So if I divide everything by x, I get 2 plus 1 over x, 3 minus 1 over x. And now I can actually see what's happening. As x goes to infinity, like if I think of x as a huge, huge number, like a million or a billion, 1 over x is basically 0. It's so close to 0 it doesn't even matter. So basically on the top is going to 2 and the bottom is going to 3 because these 1 over x's in the limit they don't matter. So this limit is 2/3. Let's try this again. And actually, okay. On the last one, maybe I gave a little bit of bad advice. It worked on the last one, but let me refine my advice here. So first of all, as x goes to negative infinity, the top, well, maybe it's hard to tell what's going on with the top, but if I'm doing x squared and 2x, then I'm dealing with huge numbers. So I get the impression that the top is going to be a huge number. The bottom, I guess, would be, I mean, if x is going to negative infinity, and I think of x as like negative a million or negative a billion, then the bottom is going to be a huge negative number. In any case, I'm going to do roughly the same thing, except, yeah, last time I said divide by the largest power of x that you see. Let me revise that. I'm going to divide by the largest power of x that I see on the bottom. So I'm not going to divide the top and bottom by x squared. I'm just going to do x. So what happens when I do that? The bottom is just this, and now the top is x plus 2 minus 3 over x. And now I should be able to tell what's going on. Again, 1 over x is going to 0. 3 over x is also going to 0. Because x is going to negative infinity. If I do 1 over negative a million, that's just a tiny negative number. So that hardly matters. So the bottom, it looks like, is just going to 1. So then what's really happening on the top is I've got this, which hardly matters, and then I've got 2, and then I'm adding this x. So if I envision plugging in a huge negative number for x, like negative a billion, it looks like the top, I'm going to have negative a billion here, I'm going to have a 2, which hardly affects negative a billion, and then I'm going to have this, which is essentially 0. So the main thing on the top is just this x. It's like negative, the top would be basically negative 1 billion or very, very close to that. Meanwhile, the bottom would just basically be 1. So if I do that, I'm getting a huge negative number. So I would say this limit is negative infinity. Let me do one more. So with this one, again, without further ado, let me divide by the largest power of x that I see on the bottom. And what happens? So x squared over x cubed, that would leave 1 over x. And then here I would have 3 plus x over x cubed would be 1 over x squared, negative 2 over x cubed. And now this one's actually easier now that I look at it again. 1 over x is going to 0. In fact, this is also going to 0, because if x is a huge number, x cubed is even bigger. So, and 7 over a humongous number is basically 0. And then what do we have on the bottom? This is basically 0. This is basically 0. Of course, there's this 3, but so what all do we have? Everything was 0 on the top. On the bottom, the only thing that wasn't 0 was just this 3. So 0. Yeah. So if you look back at these, you can see that the only thing that matters is the largest power of x on the top and the largest power of x on the bottom. In fact, once you know this shortcut, I can look at this 2x plus 1 over 3x minus 1 and say this plus 1 and this minus 1 don't matter compared to the x. So I can, if I just cover them up with my finger, I get 2x over 3x. And once I'm there, I can just cancel the x's and get 2/3. If I'm here, if I ignore everything but the biggest power of x on the top, and also ignore everything but the biggest power of x on bottom, I get x squared over x, which would cancel, and I would just get x. And I would be doing the limit as x goes to negative infinity of x. So as x goes to negative infinity, if I'm doing x, the answer should be negative infinity, and it was. Here, if I ignore everything but the biggest power of x on the top, I get that. And if I do the same on the bottom, I get that. If I'm there, I would cancel an x squared, and I would just have a 1 over 3x, right? And I would be doing 1 over 3x, and x is going to infinity. So the top is just 1, and the bottom is going to infinity, and then 1 over infinity should give me 0, and that's what I got. So feel free to use this shortcut in the future. If the top is a polynomial and the bottom is a polynomial, and the limit is x, and the limit is as x goes to infinity or negative infinity. That's important. If it's at x going to infinity or negative infinity, and you have a polynomial on the top and a polynomial on the bottom, you can do this. You can just ignore everything but the biggest power of x on the top and do the same on the bottom, and just find the limit of that, and that should be your answer. Okay, what else? So yeah, maybe there's some weird ones, like say this. The limit as x goes to infinity of this. And part of this is easy. This 1 over x squared, we know what happens to that. That goes to 0. So it all comes down to what happens with sine of x. But I'm not going to do a great job here because I don't need to. I'm just illustrating something. Here's a rough sketch of y equals sine x. And on a graph, as I'm thinking about the limit as x goes to infinity, I'm looking at the graph as I go farther and farther to the right. And yeah, so we did an example like this before where we're looking at the graph, and I could sort of tell as I go farther and farther to the right, this graph is approaching this line, this horizontal line, y equals -2. But This graph doesn't look like that. It's not flattening out the way this one did. That the graph is getting very flat and looking horizontal, whereas this one, as I go farther and farther to the right, is just going up and down and up and down. This limit, whoops, does not exist. Because the limit as x goes to infinity of sine x does not exist. There's a few similar facts, like of course the graph of cosine looks similar, at least in the sense that it goes up and down and up and down. So that limit as x goes to infinity would also not exist if it was cosine instead of sine. Of course, the limit as x goes to negative infinity, because they didn't draw this part of the graph, but it looks sort of the same going to the left. The limit as x goes to negative infinity would also not exist, and the same would be true of cosine. So, all right. Now there's a limit like this. As x goes to infinity, of course, x plus 1 is a huge number, if x is a huge number. And if I do the square root of a huge number, well, the square root of a huge number is still a huge number. Like the square root of 1,000,000 is 1,000. The square root of 1,000,000,000,000 is 1,000,000. So don't get confused by the fact that the square root of a huge number is going to be smaller than the original number. It's still what we would call a huge number. Like the square root of 1,000,000 is 1,000, and 1,000 is pretty big. So the square root of x plus 1, I'm thinking of this as growing very large. But then this is also growing very large. If x is very large, this is the square root of x, and that would be very large. So I'm taking a very large number minus another very large number, which is hard to figure out what happens when you're doing a limit. It depends how much larger is this huge number than this huge number. It's not so easy to tell just by looking. So here's what we're going to do. We're going to do some algebra, and this is actually a similar trick to what we've seen before. This is the conjugate. I'm going to make this a fraction just artificially by making the bottom a 1, and then I'm going to multiply the top and bottom by the conjugate. Like that. And how does this go? Remember, this turns into the difference of two squares. So I'm going to have this thing squared, which is just x plus 1, minus this thing squared, which is just x. And on the bottom, there's nothing to do. So I've just got this. Okay, now I've got a minus x and a plus x, so I just have 1 over this. And now I can actually tell what's happening. So keep in mind what we said before, which is that x goes to infinity. Well, let me say this more informally. The square root of a huge number is a huge number. As x goes to infinity, the square root of x plus 1 is going to infinity. The square root of x is also going to infinity. So on the bottom, what I see is a huge positive number plus a huge positive number. And here we don't have much of an issue. So let me emphasize this again. At the very beginning, when I was looking at this, like this square root minus this square root, I had a huge number minus another huge number. And what I said is it's hard to tell what's happening there. It's possible to have a huge number and subtract another huge number and have it still be huge. Like if I take 2 million minus 1 million, those are both huge numbers, but I subtract them, and the difference is still 1 million, which is still pretty huge. I can also take the difference of two huge numbers and have the difference be quite small. Like it could be 1 million 0.1 minus a million. And you know, both are huge numbers, but I take the difference, and the difference is only 0.1, which is quite small. I don't have the same issue if I'm doing a huge number plus a huge number. That's going to be huge no matter what. I don't really care which one of these is bigger than the other one. The fact that they're both huge and positive means that when I add them together, it's going to be huge and positive. So I don't have the same problem that I had up here when I look down here. The bottom is clearly going to positive infinity because I have a huge positive number plus a huge positive number. And because the top is just 1, I'm doing 1 divided by a huge positive number, which gives me a limit of 0. Okay. Let me do one more. So, oops, this is definitely supposed to be a g of x, not an f of x. So let's do the limit as x goes to infinity of g of x. If g of x is in between these two functions. So the key to this is if g is in between two functions, even if I don't know what g of x actually is, if I'm able to find the limit of this function and the limit of this function and they're the same, then g of x has to also be the same. And by the way, this is called the squeeze theorem. And it's the idea is that like g of x is squeezed between these two. Sometimes people also call this the sandwich theorem. I mean, I guess like this function is a piece of bread and this is a piece of bread and g of x is the meat or something. Anyway, we just have to find both of these limits, and if they're the same answer, then we know our answer for g. So let me do this one. And I'll use our shortcut for this. These are the top and bottom are polynomials. I'm doing x as x goes to infinity, so I can just pay attention to the biggest power of x on the top and bottom, which is x squared over x squared. Of course, that just cancels and gives me 1, so the limit is 1. So that was easy enough. Let me do this other one. Now, I can almost use the same shortcut here. I won't do it because these aren't polynomials. 2 to the x is an exponential function, and the trick I showed you is for polynomials. And you can get yourself into a little bit of danger if you go applying it to things that aren't polynomials. It's basically what's going to happen is we're going to get 1 because these things don't matter, but I won't just do it that way. Whoops, I don't want to write this equal sign. What I'm going to do is I'm going to do a trick similar to the trick where I divide the top and bottom by a power of x, except instead of a power of x, it's going to be 2 to the x. So I'm going to divide by 2 to the x, 2 to the x. So what do I get? I get 1 minus 7 over 2 to the x over 1 plus 1 over 2 to the x. And now I'm going to say, as x goes to infinity, 2 to a huge number is a huge number. Like if you do 2 to the 1/millionth power, that's actually, it's like an astronomical number. It's probably bigger than the number of atoms in the universe or something. But 2 to the 1/millionth power is huge. So as x goes to infinity, 2 to the x goes to infinity. So things like this are basically 0 if I take 7 and divide it by a huge number. So same thing here, it's basically 0. So this is what I said, we're going to get 1. And that actually is the same answer as if I'd done this, but I don't really want to, I don't want to show you how to do it that way because using that shortcut's a little bit dangerous. The safe way to do it is to do what I did here, to divide the top and bottom by 2 to the x. So in conclusion, I did the limit of this, and I got 1. I did the limit of this, and I also got 1. So this g of x, which is stuck between here and here, the limit has to also be 1. Okay.